Hello all, welcome back to ATM 5, Our Changing Atmosphere. In today's lecture, we'll be using all we've learned to date in this class by revisiting a recent weather disaster of major significance for the state of California, the California Drought of 2012 through 2016. In this section, we'll be defining ridiculously resilient ridge and snow drought. We'll be asking, what was responsible for persistent dryness in 2012 through 2016 in California? Was this drought unusual in the history of California? And was this drought a sign of things to come? As a reminder of what we know about California, California is one of the most biologically and environmentally diverse regions in the world. Agriculture in California is responsible for approximately 50% of national fruit and vegetable production in the United States. The agriculture industry in both urban and rural communities depend on snow storage and well-timed snowmelt in order to satisfy demand over the dry summer season. It is also well known that California is particularly susceptible to extreme weather events, particularly those events related to the hydrology of California, where we receive either too much precipitation or too little. California's climate is largely Mediterranean, meaning that it features wet winters and dry summers. Almost all precipitation comes in the winter months, particularly December, January, February, and March. Most of that precipitation falls in the Sierra Nevada mountains and is driven by orographic uplift. Today's lecture focuses on the California Drought of 2012 through 2016, sometimes referred to as the Drought of 2011 to 2017, even though 2011 and 2017 were relatively wet years. During this period, persistently dry conditions were experienced across the state, only for the drought to be broken up by the anomalously wet winter of 2016 to 2017. Prior to this winter, the state had accumulated a total rain debt equal to 1 year of average precipitation. That is, for many regions in California, the 4-year period from 2012 through 2016 experienced only 3 years of average precipitation. The plot here shows California's climate history back to 1950, with each water year represented by 1 bar. Water resources in California are normally quantified in terms of water years, which extend from October through September in the following year. Thus, the 2020 water year covers the period from October 2019 through September 2020. The values of each year are relative to the 1980 to 2010 mean climate. The top plot shows temperature departure, the middle shows precipitation departure, and the bottom shows Palmer Drought Severity Index, also known as PDSI. PDSI is a common index used to quantify the intensity of a drought in terms of precipitation and temperature, with more negative values corresponding to drier conditions. As can be seen from this plot, the 2014 and 2015 water years exhibited record low values of PDSI as the drought reached its peak. As can be seen from the middle plot here, California has often experienced sequentially dry years, typically punctuated by individual years of anomalous wetness. No obvious trend is apparent in the precipitation data, however. Besides being anomalously dry, the period from 2012 through 2016 was also anomalously warm, with temperatures far above the average for the 1980 to 2010 period. As discussed already, there is little doubt that the warmer temperatures experienced by the state over this period were strongly associated with climate change. The 2012 through 2016 period was bookended by 2 relatively wet years, 2011 being a somewhat wetter than average year, and 2017 being significantly wetter than average. The 2012 through 2016 drought was unlike any drought period experienced this century, and there was essentially no part of the state untouched by it. This plot shows the percentage of drought area in California from 2000 through 2017, where yellow refers to abnormally dry conditions, and more intense shades of red referring to moderate, severe, extreme, and exceptional drought. At the drought's peak in 2014, the entire state was classified as being under at least severe drought, and more than 50% of the state was experiencing exceptional drought. However, what I would like to emphasize in this lecture is that no 2 years of the drought period were alike. Each year had its own unique character, and consequently its own unique impacts. Prior to 2013, the coming drought did not appear unusual. While 2011 was wet and 2012 dry, the conditions during 2012 were fairly typical of many past drought or dry years. The period from 2013 to 2014 was essentially one of the driest periods in the state's history, with very little precipitation received over the whole winter season. The effect was a rapid descent into incredibly dry conditions with no past analog since the beginning of modern civilization. These conditions persisted into 2015. Although precipitation recovered somewhat, temperatures were far above normal and produced record low snow accumulation. A major El Nino event was forecasted for the end of 2015, which many believed would bring an end to the drought. However, the El Nino ended up being one of the strongest on record, and the storm track ended up being shifted northward beyond the borders of California. While the Pacific Northwest received record precipitation, California's drought persisted. It was only at the end of 2016 that the drought-buster year finally came, delivering twice the average amount of precipitation for California, and effectively ending the drought in only a few short months. Nonetheless, the impacts of the drought have persisted to today, particularly in the Sierra Nevada, where the drought triggered record die-off of the forests in response to soil moisture depletion. And groundwater depletion throughout the Central Valley left many communities still dry. Among the big precipitation events experienced by California over its winter season, most come in the form of atmospheric rivers, such as the one depicted here. In this image, moisture content is depicted in gray and precipitation in color. Atmospheric rivers are largely a mid-latitudinal phenomenon and are often associated with the cold fronts of extratropical cyclones. Formally, atmospheric rivers are long, narrow filaments of moisture in the atmosphere that are responsible for transporting water from the subtropics to the mid-latitudes. To give a sense of perspective, an average atmospheric river transports the equivalent of 7.5 times the average discharge of the Mississippi River, or around 10 million acre-feet per day. In the Pacific Northwest, around 25 to 35% of annual precipitation is associated with atmospheric river events. In California, the contribution is even more significant. 35 to 45% of annual precipitation here is associated with ARs. Atmospheric rivers, or rather, the absence of atmospheric rivers, is strongly associated with drought in California. Being such a large contributor to total annual precipitation, when ARs fail to impact California, the state quickly descends into drought. The lack of strong atmospheric river events was the primary contributor to dry conditions in California over the 2012 through 2016 drought period. So why were there so few atmospheric rivers? The failure of these ARs to make landfall in California can be traced in part to an atmospheric feature known as the Ridiculously Resilient Ridge, or RRR for short, a region of persistent high pressure, also known as ridging, that occurred off the coast of California from 2012 through 2016. The RRR was not a single ridging event, but instead a sequence of such events that occurred with high frequency. Because of the ridiculously resilient ridge, most atmospheric rivers during the 2013-2014 winter season were redirected northward, making landfall in Alaska and the Pacific Northwest rather than in California. This produced anomalously low precipitation throughout California, and anomalously high precipitation in the northern Pacific. The plot here shows one such snapshot of the ridiculously resilient ridge. The smooth black lines are analogous to lines of constant pressure, which, as you'll remember from our discussion of atmospheric dynamics, are also tracks or paths for atmospheric air parcels. The RRR here appears as a blob of anomalous high pressure that had the effect of pushing those tracks northward. Incoming air parcels from the west would be carried far north, where orographic uplift would squeeze out their precipitation before returning those air parcels to the south in California. But by this point, all of that precipitation had been removed, leaving the air parcels dry and unable to counter the drought. In this satellite view from January 20th, 2014 through January 24th, 2014, we see the impact of the ridiculously resilient ridge. A plume of moisture emerges in the west between 30 north and 40 north that initially appears destined for California. However, if you keep an eye on the region off the California coast, you'll notice persistent clear skies. This is a common feature of regions of high pressure such as the ridiculously resilient ridge. The plume of moisture originally destined for California is turned northward and appears almost vacuumed up towards Alaska. The path followed by the moisture on January 23rd is shown here. The high-pressure ridge is highlighted here, again characterized by clear skies. The moisture plume is heading almost directly north at this point, producing heavy precipitation along the Alaskan coast. A winter of persistently dry conditions contributed to a dramatic change in the landscape of California from the previous year. Here on the left, we see January 13th, 2013, characterized by plenty of snow and a green Central Valley. On the right is January 13th, 2014, with a diminished snowpack and dry brown soil visible throughout. The U.S. Drought Monitor provides up-to-date reporting on drought conditions across the United States, classifying regions as being normal, abnormally dry, or under one of many categories of drought. On March 4th, 2014, the record dry winter season produced drought conditions throughout the state and much of the U.S. West. Although Central California, the region between the San Francisco Bay and Los Angeles, was perhaps most heavily impacted, extreme drought was also present throughout the Central Valley and along much of the coast. Moving into 2015, some of California's wintertime precipitation returned, although precipitation still remained well below average. What was most notable about the 2015 water year was that temperatures skyrocketed and the winter season set the record for the warmest December through February. The plot on the left shows that much of the U.S. West experienced temperatures 3 to 9 degrees Fahrenheit above average, and California and most of its neighboring states experienced record-setting temperatures. This was in contrast with the eastern U.S., which experienced relatively cooler temperatures during this time. This contrasting behavior between east and west is a common occurrence known as the North American dipole. With low precipitation and record high temperatures, the water year 2015 snowpack fell to the lowest level on record, approximately 95% below average. This made it the fourth consecutive year with below average snowpack. Satellite images from water years 2014 and 2015 are seen here. Although precipitation made for a much greener Central Valley compared to the previous year, snowpack was much reduced, particularly in the lower-lying areas of the Northern Sierra and the Klamath. A loss of snowpack is typically responsible for drier summertime conditions and depleted soil moisture. The 2014 to 2015 winter season was exemplary of what is known as a snow drought. Formally, a snow drought is a period of below-average snowpack, typically differentiated into two categories: a dry snow drought associated with insufficient precipitation and consequently insufficient snowfall to allow snowpack accumulation, and a wet snow drought associated with above-average temperatures that cause precipitation to fall as rain instead of snow, and thus prevent snowpack accumulation. While 2015 wouldn't necessarily be considered a wet year, it was nonetheless characterized by incredibly low snowpack. This term snow drought is very important going forward, as we anticipate much of the 21st century will be existing in a state of wet snow drought. By October 2015, exceptional drought was present throughout the state, from the Central Coast to the northern Sierra Nevada mountains. Effectively, the entire U.S. west of Colorado, was considered in some state of drought. In the summer of 2015, warmer eastern Pacific temperatures emerged, characteristic of what is known as an El Niño pattern. Scientists predicted that an exceptionally strong El Niño was on its way for the coming winter season. Because of a moister Pacific environment and an enhanced Hadley circulation, past El Niño events have sometimes been associated with wetter conditions in California. And so there was hope that the El Niño would bring relief from the drought. A long-held belief is that El Niño events themselves are associated with significant precipitation in California. However, beyond the southernmost reaches of California, there is actually only a weak association between El Niño years and precipitation in the state. The map here shows the statistically significant effects of an El Niño warm event on global temperatures and precipitation. Along the periphery of the Pacific, we generally see warm temperatures associated with El Niño conditions. Primarily, El Niño is associated with wet and warm conditions through the tropical Pacific and corresponding dryness over Indonesia. In the U.S., El Niño is associated with wet and cool conditions throughout the southern U.S., and wet conditions in Arizona and the U.S. Southwest. Notably absent is a strong association between El Niño and precipitation in central or northern California. Nonetheless, with the strong El Niño, the NOAA Climate Prediction Center did post a seasonal forecast that suggested wet conditions throughout California in the winter of 2015 through 2016. This forecast was considered by many a great failure, as the actual precipitation received along the U.S. West Coast was effectively opposite to what was predicted. Namely, NOAA predicted an above-average likelihood of precipitation in California and a below-average likelihood in the Pacific Northwest. However, what was received was below-average precipitation in California and record-breaking precipitation in the Pacific Northwest. This year was associated with widespread flooding in Washington and continued drought in California. To understand what happened, we need to be both aware that an El Nino event is not a particularly predictive event when it comes to precipitation in California, and also be aware that this particular El Nino was unlike any that had been seen before. Daniel Swain stated it well on his Weather West blog. Depending on how you measure it, the 2015 to 2016 El Nino is either the strongest or among the strongest events in the observed record going back to at least 1950. The Pacific warmed, tropical thunderstorms increased, the Hadley cell strengthened, the Pacific jet began to roar. But this year, the Hadley cell was actually strengthened a bit more than expected. The descending air on its northern side has occurred closer to California, which means that enhanced temperature differential is occurring farther to the north than during previous big El Nino events. So while NOAA had predicted that the storm track would be found close to the San Francisco Bay, the actual storm track was instead pointed at the Pacific Northwest. The subsiding branch of the Hadley circulation was pushed northward, and a good part of that subsidence occurred over Southern California. Under such a vigorous Hadley circulation, California found itself again experiencing a year of abnormally low precipitation. After nearly 5 years of continuous drought, it was the winter season at the end of 2016 that finally brought the state out of drought. As mentioned earlier, before this winter season, California had racked up an accumulated rain debt equal to 1 year of average precipitation. That meant that double the average precipitation would be needed to return the state to normal conditions. When I was asked in the fall of 2016 whether or not this winter would finally be the one to bring us out, I was reluctant to commit, and stated how unlikely it would be to have a year with so much rain. But it had happened before. The abnormally wet 1983 water year did provide slightly more than double average precipitation. Surprisingly, in this winter season, the state recorded precipitation that was either record-breaking or in the top 10% of all years for almost the entire state north of Los Angeles. Southern California even experienced precipitation that was above average. In one winter season, the rain debt was effectively wiped out for much of the state, except its most southernmost reaches. By April 2017, the U.S. Drought Monitor reported an emergence from drought for much of California, although pockets remained along the central and southern California coasts. The difference over that single winter season was striking. Recovery from the drought was both unexpected and timely. Nonetheless, the repercussions of the drought remained, including widespread die-off in the Sierra Nevada forests and severely depleted groundwater reserves. These impacts have been felt even today. Two key questions emerge naturally from this review. First, was this drought unusual in the history of California? And second, is this drought a sign of things to come? The answer to the first question depends strongly on what time period is being referred to. Looking at the Palmer Drought Severity Index for California from 1895 through 2014, we see that no past drought has reached the magnitude of dryness observed in 2014. So it could be easily argued that in the history of California's recorded climate, this event was unprecedented. However, if we look back at the paleoclimate record of the U.S. West, there is evidence that droughts of even greater severity have occurred over the past millennium. We had touched on this a bit in Lecture 4. Tree ring records have been successfully used to reconstruct the recent climate of the U.S. West, revealing that there were occasional periods of intense, prolonged dryness referred to as megadroughts. To quote, "A remarkable network of centuries-long annual tree ring chronologies has now allowed for the reconstruction of past drought over North America, covering the past 1,000 or more years in most regions. These reconstructions revealed the occurrence of past megadroughts of unprecedented severity and duration, ones that have never been experienced by modern societies in North America. There is strong archaeological evidence for the destabilizing influence of these past droughts on advanced agricultural societies, examples that should resonate today given the increasing vulnerability of modern water-based systems to relatively short-term droughts. The period since the 1500s has been a relatively wet period for California. However, before the 1500s, several major drought events have been identified which feature widespread drought throughout the U.S. West. It is entirely likely that these periods featured shorter dry periods with drought severity that exceeded that of the 2012 through 2016 period. Thus, we can say it is likely that this recent drought is not unprecedented in the climate record of the past 1,000 years, although the anomalously high temperatures accompanying this particular drought are certainly in part due to human influences. Notably, in this figure is the short uptick visible at the end of the plot. Although it's hardly enough evidence to draw a solid conclusion, there remains the possibility that the climate of California may be shifting back into a drier state or kicking off a new megadrought. Along those lines, the second key question we would like to ask is this drought a sign of things to come? Namely, will extreme droughts of this nature be commonplace in California over the next century? To answer this question, we need to assess two competing drivers of drought, thermodynamics and dynamics. The first factor refers to the fact that warmer air holds more moisture, and hence tends to dump out more precipitation when a precipitation event occurs. As we've studied previously, this will drive increased wetness in Northern California. The second factor refers to features such as the ridiculously resilient ridge, which was a primary driver in the rapid descent into drought over the 2013 to 2014 winter season. These two factors were investigated by Wong and Schubert over the historical record in their paper cited here. So what did they find? In the bottom left figure here, they did find that water vapor has increased compared to nearly a century prior to today. In the bottom right figure, they did find that the ridging has also increased in frequency. However, because of these counteracting effects, the total change in precipitation in California, shown here in the top left, has basically been zero. Simultaneously, air temperatures have steadily increased, and there is an obvious difference between warm, modern air temperatures and those from history. The conclusions of this study are straightforward. Namely, the 2013 sea surface temperature anomalies produced a predilection for California drought, whereas the long-term warming trend appeared to make no appreciable contributions because of the counteraction between its dynamical and thermodynamic effects. So if one focuses exclusively on precipitation amounts, California has experienced effectively no change because of these counteracting factors. With that said, other studies have shown that the temperature increase also has the potential to drive more rapid shifts between dry and wet states. So while to date there has not been a change in the probability of such a drought, warming temperatures have the potential to exacerbate future droughts or lead to less warning on the next one. In summary, there are a few take-home messages from this drought that is necessary to guide future management decisions in California. We know California lives in the extreme. That is, extreme weather is common in our state. Looking back, we often find ourselves either with an abundance of precipitation or in a drought. Temperature increases from climate change will certainly lead to warmer temperatures, a depletion of snowpack, more dry days, but more extreme rains when they do come. If you're interested in learning more about the California drought, you can check out some of the work we've completed on this topic. In particular, you can check out our paper, California's Drought of the Future, a mid-century recreation of the exceptional conditions of 2012 through 2017, which examines the past drought and examines how an analogous drought would play out in the middle of the century. If you're interested in how California is working to manage the next drought, you can check out this piece led by Jeff Mount at the Public Policy Institute of California. The 2012 through 2016 drought was an extreme event with significant implications on the whole state of California. While it led to massive forest die-off and severely depleted aquifers, it also motivated new legislation on groundwater, the Sustainable Groundwater Management Act, or SGMA. There is hope that with proper management and buy-in from stakeholders across the state, that we will be prepared for the next drought, even as climate change continues to complicate matters. In the next lecture, we'll stay on this topic of extreme weather in California and focus on how climate change is impacting a wide range of extreme weather.